this is Victoria again.
Hi again. I would like to introduce Hassan Tamar from Intel, and he's going to talk about the SVT AV1. Please.
All right, cool. Hello, everyone. Hope everyone had a great bite. I definitely enjoyed it. I was hungry. All right, so my name is Hassan Tamar, and I'm the product lead at Intel for SVT. Today, I'll share with you guys an overview of SVT AV1, its latest performance results and roadmap. I wanted to also introduce the Open Visual Cloud, which SVT is only a part of, and this is the larger project that Intel is driving in the Visual Cloud. And so I'm gonna start quickly with that overview. And to talk about that, let's start with talking about media and how media has been transforming. It has been undergoing a rapid evolution. It's not anymore the stream that you get at your TV while sitting at your living room. It's grown to much more than that. The content is becoming richer. It's more immersive and interactive. It's delivered globally, and often with quite a bit of intelligence into it to personalize the user experience. And as we have seen this switch between a passive consumption of media into really an intelligent visual experience, Intel wanted to take into the Visual Cloud an optimization of 5 main workloads. When we said media before in the Visual Cloud, we really wanted to say media processing and delivery. Nowadays, it has been evolved into much more than that, so we could find media analytics where the content is actually being analyzed to allow for some applications such as ads insertion in a smart way while you're watching the content. Immersive media where the content is augmented, and now you're not watching the video anymore, but you are actually experiencing the video, which is just awesome, actually. Cloud graphics is adding the ability for content editors to use the cloud infrastructure and the cloud compute power to be able to edit and create their rich content on the cloud and remote access it without, a lot of delays. And cloud gaming, as Yoshi was mentioning, is another booming industry where things are going really fast to the point where you now are able to watch game streaming on any really connected platform. In order to allow for these 5 workloads, we need really, and maybe we're simplifying it too much, but we need 4 building blocks to allow for that: decode, inference, rendering, and encode. These building blocks are not always used. In some cases, they are. They are. In some other cases, part of which are not used. But as you can see, that encode is used in all of these workloads. And what we based the strategy and the problem solving here on is that we should really start with software first, because this is where the first adoptions of the technology are. Adding optimizations to software on CPUs, then we can move to GPUs, accelerators, is really a key aspect to it, and create some reference pipelines where we show all of these blocks working together. Taking all of this to open source to the community would, first of all, make the adoption of it very, very easy. Make the proof of concept basically right there, so that customers and users are able to use these reference pipelines. We try to create a robust ecosystem and healthy ecosystem around it, as many of the other companies are doing, and we are trying to subsidize and empower our partners to use these reference pipelines and implement their applications on them. And now Intel is targeting key applications for their solutions rather than doing very general, aspect deployment. So introducing the Open Visual Cloud, we sat down with a lot of customers. We got a lot of feedback, even with the regular users, and we saw that there is a need for a reference kind of implementation that puts together these building blocks to showcase how we can manage CPU resources, hardware resources, and put everything in the pipeline and make sure it works. With that, Intel is trying to produce and optimize the 4 core building blocks of these workloads. We are trying to support the industry frameworks in the open source, such as FFmpeg, GStreamer, OpenVINO, TensorFlow, hardware and software building blocks, and Intel is providing both. The reference pipelines are all in the open source, and you could access them on GitHub. And for software encoders, we're using the SVT suite, which we're going to be talking about fairly soon. So with that, right now, there are a couple of reference pipelines that are ready on the GitHub project of the Open Visual Cloud. One of them is the CDN live streaming, and the other one is the ad insertion. They're both using many components. You could use SVT, you could use other things in there too. We are working on producing a reference pipeline for 360 VR video and the interactive ray tracing for the the content editing. And as you can see, all of the 4 building blocks are there, represented by multiple components into this, and the whole reference pipeline is working end to end, and it's all open source and under very permissive license. So moving to scalable video technology, or SVT. So I'm gonna start first with an introduction of SVT. What is SVT? SVT, when we say SVT, it's more of an architecture. It's a software architecture, and I personally would like to think of it as a philosophy of building software codecs, because it's not really always about what the standard gives you. It's about the architecture and how it deals with the standards. So SVT is a standard agnostic software encoder architecture. We designed it so that it's easy to use. It's kind of block-based, like you're putting Lego together, and you could put the Lego wherever you want. To some extent, you can get creative with it. It's fully scalable, because now we're seeing that the number of cores is growing much more than the frequency utilization, and so we are trying to use up those cores as much as possible. And it's really optimized for multiple presets, going all the way. The spectrum goes all the way from the best quality to the fastest speed. SVT features in that context 3 main features that I will try to tie to how we can get coding efficiency gains and speed gains based on these features, in conjunction with the codecs themselves. So there's a multi-dimensional parallelism that we can use in there, RD optimized classification, and resource adaptive scalability. So we're going to go into a little bit of detail over every one of these. So for parallelism, SVT employs 3 levels of parallelism, or 3 types. The first one is picture-based parallelism, which is used usually in some applications where we could be allowed a certain level of latency and and be able to encode multiple pictures at the same time. Although that's not the main parallelism that we use, is actually the process-based parallelism, which is one of the key features of SVT. So we split the encoding stages into multiple processes. At each process, we do a certain level of approximation. It does not have to be very accurate at each level until you hit the last level, where everything has to be done on reconstructed pictures. All of the boundaries have to be respected, and all of the ordering has to be respected. So every block could be divided into sub-blocks. We could see the analysis phase, where we can do some motion estimation. We could do some detection. We could do a lot of the key aspects that the previous presentations have talked about, to allow for the encoder to make smarter decisions that would both save you speed cycle or cycle count and also quality, because sometimes using a feature does not essentially mean you get quality out of it. So that's the trade-off that we are playing. Moving on, we go into the mode decision where it becomes a little, you know, more restrictive, where we have to do more, where we have to employ more accurate tools to choose the modes, choose the partitioning. But even with that, we can still do some approximation down to the level of the encode pass, where we can't really afford to do things out of order or out of hand, and we have to respect a certain level of ordering and a certain level of dependency. And so segment-based parallelism is the next level of parallelism that actually ties into the first one, because this is a sub-picture parallelism, which could be down to the super block, down to the LCU in HEVC, for example, or even smaller in AVC. And the idea here is at each level of the processing, if we are allowed to go, for example, if we do motion estimation on source pictures, then we don't really have any boundaries, we don't have any restrictions, and so we can do motion estimation on every block all at the same time, and so that fills up the CPU quite quickly. Now, moving down to the mode decision, we still have some more restrictions. However, we can do things in a non-normative way because it's still an encoder choice at that level. Down when it becomes a you know, an ordering and a standard you know, issue where the ordering and the dependencies are respected, it becomes more like a wavefront, similar to the wavefront you know, techniques of HEVC. However, this is a lossless technique, so it does not come with coding efficiency losses. So you would be able to use this technique whether you use one segment or multiple segments. You get approximately the same bit stream. You could use tiles within this, with this. You could use slices with it or without it. And so this is yet another way to allow us to shrink down on the latency as much as possible. Again, working with the previous way of doing the parallelism, where we basically split the multiple encoding stages into processes. So now, another key feature of SVT, that it is the RD optimized classification. And so again, this is one of the aspects where a codec agnostic tool does not really have to go with the standard. And so we take each picture, we analyze that picture, and based on the characteristic of that picture, we choose the set of features that may make sense for that content. And because, as I said, not every feature does give you a gain, because at every stage of the encoding, you might have a feature that in that kind of content does not give you a lot of gain. And so, again, we faced these in multiple ways. In the SVT HEVC you know, development, we faced some pictures or some content where applying some filters, for example, is actually hurting more than helping. And mainly, we see this in both subjective quality and the, you know, the reference metrics that we employ. And so making sure that we divide and subdivide the picture into multiple regions of interest, we analyze that picture, we do that selection, and based on that, the mode decision will have some more insight on making much better you know, mode decisions, whether it will save cycles and give an extra quality gain. That's definitely both are possible with the SVT architecture. Another way of you know, going a little lower on that, and it's basically the cost of running video encoders nowadays is not only running cycles, it's also memory, right? And so to knock down a lot of the memory costs, you could do some approximations based on a lower or increasing the CHROMINANCE subsampling down to from 422 to 420, and down from 8-bit to 10-bit, or sorry, from 10-bit to 8-bit. And so we tend to keep track of all of these formats throughout the encode and choose whichever would give us the best quality trade-off or speed trade-off at every point of the way. And so all of this is available in SVT and applicable when is needed. And so you can take away a 422 component, put a 420, and be able to still work your way through. However, at the very end, of course, you need to produce a 422 bit stream, and so the last stage would have to be the superset of all of these features. Another level of data efficiency processing is at some early stages of the mode decision and the encode, you don't really have to use all of the coefficients, and so you could be a little smart about how where the saturation of energy is at. And so if you find out that the most of the saturation is at the top left corner of the block, you could do a partial transform of the block and keep only the top left corner in this case, or if the block is bigger, you could keep more than that. And based on the classification that we do at the beginning, we would know which blocks are prone to actually a lot of noise. In this case, noise might make your decision much more, I would say, harder, and it would have that layer of error that you could use when removing that. It's really a way of filtering to some extent to protect your mode decision, and to that extent you would be able to make a better mode decision, whether it's mode partitioning or what have you. So moving on to again, another way of classification, which in this case, based on the region of interest, we have an algorithm called adaptive ADP, adaptive depth partitioning. That adaptive partitioning, it starts based on the information that it gets from the picture itself, and it tells the mode decision where to start when it comes to partitioning. That way, sometimes when you do, using the regular metrics, you might actually make a mistake in quality because of noise, because of many aspects in the video that might make that decision not very accurate. And so if you tell it beforehand with some level of intelligence that, hey, this block is very, very likely gonna be a small block partitioning because of edges, because of texture, because of sharpness, because of whatever you wanna convey in there, then it is much easier for you to make that decision, and you can safely ignore part of the partitioning. And so this is yet another way of making these smart decisions. Of course, these decisions do not come for free. They come with a certain level of tools that need to be in there to allow for these smart decisions, and we'll go into some of the tools that do that later in AV1. The last aspect for SVT is how we can actually create a multiple set of presets, going all the way from the best quality to the fastest preset. SVT HEVC has approximately 13 presets, and we try to map those to specific applications. It is always hard to go directly into the application, but this is, we believe, a good starting point for somebody who would like to take this and customize the implementation for their specific application and make a vertical out of it. So that's for SVT in general. That could be applied to any codec, really. And now moving into SVT AV1, where we started with that architecture. And as AV1 has been challenged to produce real-time quality or real-time performance and all of those gains, we took on that challenge. We spread the cheer of AV1, spread the cheer of SVT to AV1, and we partnered with Netflix to actually start based on a scalable architecture and try to get the competitive compression efficiency to allow for AV1 to succeed in the commercial deployments. We're hoping to convey the easier to use code base and API level of APIs, and we actually also added a research decoder in there, and so it's using the same libraries as the encoder that apply, and it will make it easy for people to actually, for future codecs, to make experiments on specific tools by changing those common libraries. Now, at NAB of 2019, we launched SVT AV1 with Intel and Netflix. We brought it to the open source under GitHub. Our GM LinComp and David Dronka from Netflix have made quite a cool keynote to launch the SVT AV1. We got a lot of articles published about it, and we're getting a lot of community traction with it, and that is great. We also did a little technical presentation similar to this one to showcase what SVT is about, or to explain a little bit more about SVT. And now for the part that many people are waiting for, where is SVT at right now, SVT AV1 specifically? And so this graph is showing the coding efficiency on the y-axis as compared to libaum of CPU 0. We're using it as a reference right now. But we're hoping with the SVT advantage, we would be able to go even further than that reference. So right now we're still under development, showing every single point in that graph is an SVT preset. The top, the top graph shows where we were in March for all of the SVT AV1 presets. The bottom line, the blue line, shows where we are in June. So this is approximately a quarter worth of work. We have managed to get approximately 27% coding efficiency gains down at the best quality levels, and that even translated into the higher speed levels, where we see that we both increase the speed and the coding efficiency gain, and this is on both. This specific case is running on an AWS instance, running a dual platinum, Xeon Platinum 8124 processor, and this is showing the average PSNR and SSIM in YAV. The x-axis is right now putting as a reference the 720p speed, and so we could see that on the higher preset end, we're running 720p at about 100 FPS with the approximate quality level or BD rate level as CPU 8 of 2 pass of libaum. So zooming a little more into the lower end, where we think that this is where most of the work is going, the higher quality end is where most of the optimizations are going to go through, because we're still implementing some of the features here. SVT AV1 being a single pass implementation is actually now approximately 5% better in coding efficiency than the libaum one pass CPU 0, and it's also a little faster too. And so also we still have a little bit of a gap with CPU 0 of 2 pass, and we are planning to address that even without implementing the 2 pass. And so moving on, this is basically where the features that we are working on in this quarter and the next quarter will be, and we believe that 3 to 4% of the non-completed features. I actually just got an email from the guys saying that we already reached that 3% with only 2 features, so we're hoping for more now. And 7 to 8% is really plugging in those SVT features into the newly added AV1 tools, and this is where I would like to convey that it doesn't really matter how many features that you have in there, as long as you have a really smart engine to drive it. You need to be able to use that smartness and intelligence to use the tool's efficiency. So we might not be able to complete all of the AV1 tools at this point, but we are very confident that whatever we implement will be able to add enough coding efficiency gains to get us to the level where we could use AV1 to start deploying in both the VOD and the real-time scenarios. Now going into a little bit of a short-term roadmap for this year, we're planning to keep working on the AV1 outstanding AV1 tools. Again, the ones that make sense to implement at this point, not the ones that would drive complexity 3 times lower and give us a 0.1% gain. You know, we are targeting to hit the same BD rate levels for the best quality as libAUM of 2 pass or achieve it or exceed that. The decoder implementation is underway, and we're hoping that we will be able to finish that throughout the 3rd quarter or 4th quarter. This is specifically a you know, an effort that Netflix is championing, and we're very close on that. We already started to see some interframes supported for that decoder. We're hoping to complete some unit test coverage. You know, right now we're at about 39% approximately, so we're hoping to get as close as possible to 100% of coverage in there. Again, optimizing the trade-offs from 0 to 8, from the best quality to the highest speed is going to be always our target, and so we will be working hard on that too. Improving the coding development practices on GitHub, which has been a bit of a challenge for our teams, going from a closed source model to an open source model. And I'd like to take the opportunity to thank everybody who's posted an issue on GitHub or has given us some good constructive feedback that we can improve on. And so we're listening and trying to improve on that feedback too. And we really want to make this and the other Open Visual Cloud projects like a community project, not really an Intel or Netflix project. We're also targeting to add some more documentation to help accelerate the development and get more contributions into the game. So finally, SVT could be found under the open source and the common open source frameworks, such as the FFmpeg GStreamer. SVT HEVC is actually plugged into X265, and so you would be able to run the SVT HEVC library from the X265 library by just hooking up the libraries and running it. It's already in there, going into the 3.1, I believe, release. SVT has a sample application that's almost very similar to in all of the SVT products, HEVC, AV1, and VP9. And so this is where you could find it. The cool thing about this is that the SVT library is always licensed under a BSD plus patent, very permissive license, so you can use it. You don't have to contribute back. We would like you to contribute back, but you don't really have to by a license term. So in summary, we talked a bit today about the Open Visual Cloud, SVT in general, and I'm sorry that kind of shifted a little down, SVT AV1 and VP9, and this is where you can find more information about every one of these projects. They're all on GitHub. All of the implementations is there. If you have any questions or any issues, please feel free to post them. I don't mind seeing a lot of issues and having to always work on addressing that. That means we're always improving. There's also a white paper for SVT on one.org and a big page of the Open Visual Cloud where it shows all of the projects that the Open Visual Cloud is working on right now. This is me, and this is it. Any questions? Thank you.
Thank you so much. We didn't seem to have any questions from the remote participants, but do we have any questions from the room here while we're here? All right, let me run around 1 second. A question here from Oliver.
Thanks. I saw that you said that you're working on SVT AVC 264. What's the motivation for that?
So we are planning to work on SVT AVC. It's not there yet. The motivation for that is, I guess you have seen a couple of presentations where AVC is deemed going to last for a while, and usually when the codec is really at the end of its life, then it becomes mostly done in software. And so we're trying to get that offering out there for a complete offering of SVT, first of all. And the second is to be able to support SVT whenever it's needed in software whenever it's not actually available in hardware. So that's why.
All right. Did we have any more questions from down the front here?
So I just occurred to my mind that my understanding of the difference between hardware encoder like ASIC or and the software is the hardware they can for like a different mode, for example, like 50 intra mode or 4x4, 8x8 or this mode. They have specific hardware so that they can do the search in parallel. Right. But the software, I'm not sure they can do in parallel, but I understand you have other parallelization measures. So I don't know whether you have a point, like a data to compare if the hardware can do that level of parallelization versus the software parallelization. So with regard to live encoding, what's the pros and cons?
Right. That's always going to be one of the questions we get for software encoders. The quick answer is no, I don't really have any points of view, but what I can comment on is in software we can do, and actually one of the SVT advantages is taking the same block, you would be able to run multiple things in parallel because you are just reading to some extent and saving into some picture structures. And so that allows you to be able to test multiple modes at the same time even. So we can increase the encoding stages vertically and horizontally. And that way it would allow us to even, you could mimic a 2-pass and run a certain amount of modes in here, a certain amount of modes in here, and get the best out of it. Right now we do it vertically, and so we try a certain set of modes at the beginning, and then we try another set of modes later on, but there's nothing that will stop us from doing it in parallel.
Great. I think that is all the questions we have. Thank you so much for
Cool. Thank you for
the presentation.
having me.
Thank you.
Thanks.